the equilibrium law. In this video, we're going to introduce the concepts of the equilibrium law and the equilibrium constant, as well as the reaction quotient, and look at how we can go from the balanced simple equation to these equations for these different constants, as well as the physical meaning of these constants. Okay, so the equilibrium law itself is essentially an equation that describes something called the equilibrium constant, which we'll introduce properly on the next slide. And we can actually get this law directly from the balanced simple equation of the reaction in question. So if we took a well-known equilibrium like the Haber process, we have nitrogen and hydrogen gas in equilibrium with ammonia gas. It's a very common industrial process. And a good example of an equilibrium is this reaction doesn't go anywhere near to completion. There's still very much significant amounts of reactants and products at equilibrium. And if we wanted to write the equilibrium law for this equilibrium, we always start in the same way. The equilibrium law is describing some constant, Kc, the equilibrium constant for this reaction, but whatever reaction it refers to will always be written as Kc. And the way we construct the equilibrium law is by taking the concentrations of our products raised to their stoichiometric powers in the numerator of a fraction, and then the concentrations of our reactants raised to their stoichiometric powers in the denominator of a fraction. So in the numerator, in this case, we have ammonia. That's our only product, and it's going to be raised to its stoichiometric power, i.e. it's going to be squared in this case. In the denominator, we have our reactants. That means we have nitrogen gas and hydrogen gas. The nitrogen gas concentration is just going to be raised to the power of 1 because we only have 1 mole of N2. The hydrogen gas concentration is going to be raised to the power of 3 because we have 3 moles of hydrogen gas. Just need to extend that line. And this is our equilibrium law for the Haber process. The concentrations of our products, in this case just ammonia, raised to their stoichiometric powers over the concentrations of our reactants raised to their stoichiometric powers. And so if we allow this reaction to go to equilibrium for a given input amount of nitrogen and hydrogen, or a given amount of ammonia, we allow it to reach the point where the concentrations become constant, and then we take those concentrations of N2, H2, NH3 and put them into this equation, we will get some constant, and that constant tells us something about this equilibrium. But what exactly did it tell us about this equilibrium? Well, to understand that properly, we're going to need to think more about what the equilibrium constant actually is. The equilibrium constant gives an indication of the extent of the reaction at equilibrium. It gives you an indication of how far shifted you are to products or how far shifted you are to reactants. So a large equilibrium constant means that our numerator is much larger than our denominator. Our numerator is where our products are, our denominator is where our reactants are. So it implies that our equilibrium implies that we reach equilibrium with a mixture that contains mostly products. Our reaction has gone close to completion. So if we take an example of a reaction that pretty much goes to completion, like the oxidation of zinc by copper, in this case, when we allow this reaction to go to equilibrium, and then we calculate the value of the equilibrium constant, it comes to about 1.8 times 10 to the 37, which is extremely high and implies that our reaction has gone almost all the way to completion. We probably wouldn't even consider this an equilibrium because our position of equilibrium is so far shifted towards our products that the reaction has essentially just gone to completion. We take the flip side of this. If we have a small equilibrium constant, that indicates our mixture will contain mostly reactants. So if we take an example of a reaction that's quite fast shifted to the left, like the dissociation of ethanoic acid, in this case our equilibrium constant comes out as 1.8 times 10 to the minus 5. So in this case we've got an equilibrium that's quite fast shifted towards our reactants, where the reaction, the formation of products, doesn't actually occur very much before we reach the equilibrium position. The fact that our equilibrium constant is so small means that in our equilibrium law, our denominator must be much larger than our numerator. Therefore, we've got mostly reactants at the position of equilibrium. The equilibrium constants vary across a massive range. They'll never be lower than 0, but there's really no limit to how high they can go. And the midpoint for an equilibrium constant, for a reaction that has similar amounts of reactants and products present at the position of equilibrium, is 1. So if your equilibrium constant is around 1, that means you're looking at a sort of a equilibrium situation where you have similar concentrations of reactants and products. Now you may notice I haven't actually given units in either of these cases. The reason being that there are no consistent units for the equilibrium constant. You actually need to figure them out based on the specific equilibrium that you are looking at. Because the equilibrium law always takes a different form for a different reaction, the equilibrium constant can have different units. So if we take the example on the previous slide, where we said for the Haber process, our equilibrium constant is equal to the concentration of NH3 squared over the concentration of N2 times the concentration of H2 to the power of 3. We know that all of our concentrations are going to be measured in units of moles per decimeter cubed. So we have a concentration squared here, so the units of the numerator are going to be moles squared per decimeter to the minus 6. All we've done is squared the units of concentration because we've got that 2 in the indice. On the bottom we have the units for N2, which are just moles per decimeter cubed. And then we have the units for the concentration of H2 cubed. So that's going to be moles to the power of 3 and decimeters to the minus 9. If we think about cancelling those units out, we can cancel out 1 lot of the moles per decimeter cubed up here using the units for the N2. We can then cancel out these top units completely with the moles cubed per decimeter to the minus 9 on the bottom, and all we end up now with is essentially 1 over moles squared decimeters to the minus 6. So when we flip the denominator into the numerator, we just change the sign on the powers. So the units of our equilibrium constant in this case will be moles to the minus 2, decimeters to the 6. You can check these ones yourself, but in this case, in the case of the zinc and copper reaction, our equilibrium constant doesn't actually have any units. And in the case of the dissociation of ethanoic acid into the ethanoate ion and H+, our units are going to be moles per decimeter cubed. And the final thing to point out is just that the equilibrium constant is temperature dependent. We'll talk about exactly how temperature shifts the equilibrium constant in a later video. So the last thing to define is the reaction quotient. And the reaction quotient is heavily related to the equilibrium law and the equilibrium constant because essentially it is just the value of the equilibrium law at non-equilibrium concentrations of reactants and products. So taking the Haber process again, so at equilibrium, when our concentrations of NH3, N2 and H2 are constant, this equation will give you a constant value that gives you an impression of how far your equilibrium is shifted to the left or right. However, before you reach equilibrium, when your concentrations are still changing, you can calculate the value of this equation at any given time, and it will give you something called the reaction quotient. So hopefully you'll recall that when we have an equilibrium, we expect the concentration of our reactants to decrease, the concentration of our products to increase up to the point where they plateau and become constant. So in this case, we have the concentration of our reactants shown in blue, the concentration of our products shown in green. Concentration of our reactants starts off high, decreases to some constant value. Concentration of our reactants starts off low, increases to some constant value. At the point where they plateau, where they become completely flat, after this, we are at equilibrium. Before that, we're just approaching equilibrium, but we're not actually at our equilibrium concentrations yet. So in this part of the graph, we're just approaching equilibrium. What that means is that after this line, we're talking about Kc. Before this line, we're talking about Q, the reaction quotient. And so whereas Kc is always a constant, Q is able to change as the concentrations of reactants and products change. So we can imagine at the beginning of our reaction, we've got lots of reactants, so high concentrations in our denominator, and no products, i.e. low concentrations in our numerator. So Q is going to start off very small. In fact, it's going to start from effectively 0. And then as our reactants are used up and our denominator becomes smaller and our products are produced, the reaction quotient is going to increase. And as with seemingly all things when it comes to equilibrium, it's going to increase quickly at first, and then it's going to plateau. And we find that the value it plateaus to is going to be equal to the equilibrium constant. So we plateau to some value, and that value we plateau to is the equilibrium constant, because our reaction is going to slow down, the concentrations are going to change more and more slowly until the point that they reach their equilibrium concentrations. And at their equilibrium concentrations, we no longer think about the reaction quotient, we think about the equilibrium constant. But the quotient has been approaching the equilibrium constant the whole time. And the point where it reaches the equilibrium constant, that's when we're at equilibrium. Okay, key points to take home from this video. We saw that the equilibrium law is just given by the concentrations of the products raised to their stoichiometric powers over the concentrations of the reactants raised to their stoichiometric powers, and you have a general form of that equation here. It gives you an expression for the equilibrium constant Kc. It gives the value of the equilibrium constant when you put in the concentrations of the reactants and products at equilibrium. That equilibrium constant gives an indication of the extent of the reaction, with 1 being your central point. High values meaning you've got lots of product at equilibrium, low values meaning you've got mostly reactant at equilibrium. The reaction quotient is the value of this expression, the equilibrium law expression, for non-equilibrium concentrations. What that means is the reaction quotient is able to change. It's not a constant. However, as time progresses and your concentrations approach their equilibrium concentrations, the reaction quotient approaches the equilibrium constant.